Hello everyone, we now share our system for detecting AI-generated images. This project aims to develop a system for detecting the authenticity of images and preventing the misuse of technology due to advanced images editing techniques. To achieve this, we use models that combine CNNs with natural feature extractions to detect image authenticity. CNNs are highly effective in images classification and detection tasks, capable of automatically extracting deep features from images. Meanwhile, manufacturers' extraction methods, such as color histogram analysis, artifact detection, and boundary blur detection, offer unique insights into image texture, artifacts, and the levels of blur. By integrating these two types of features, the model can be better identify fake images, resulting in the improved accuracy and robustness. This project's techniques innovation is reflected into two key aspects. The first aspect is customer feature extraction and input fusion. Customer feature extraction involves realizing images to fixed size for CNN input. These manually extracted features are combined into one-dimension feature vector and used together with CNN features during training. In the model, image features are passed into CNN, while manually extracted features are processed through a separate input layer. The CNN and the manufacturers are then fused through a connected layer. The second aspect is fusion architecture with weight adjustment. We use weighted mechanism in the model, assigning 90% weight to CNN features and 10% to manual features. This ensures that CNN plays a dominant role in features extraction, while manual features provide additional support. After combining the two feature sets, the model is trained through fully connected layer and an output layer. The training process uses item optimizer and binary cross entropy loss function, optimizing the model's prediction based on the true label of the input date. During training, the model continuously adjusts its parameters to effectively utilize both feature size, maximizing the accuracy and the robustness of image authenticity detection. About attractive of the project. The uniqueness of the project lies is by model feature extraction and detection mechanism. This approach is more robust than deep learning model alone, particularly when handling low-quality images, artifacts, or image with highly complex processing. Manual features offer additionally value insights in those sources. By adjusting the weight ratio, the contributions of mental and CNN features are balanced in the model, ensuring optimal performance. As mentioned above, manual feature extraction includes image color histogram analysis, image artifact detection, and boundary fuzzy detection. First, by plotting the histogram, we can find that the distribution of pixel value for different color channel in the image, which helps to find out if there are any specific color features in the image. For example, if the distribution of a color channel is in an image is significantly different from what is expected, it may suggest that the image has been modified or generated. And we use edge detection to identify artifacts in an image. Involves detecting unnatural textures or edges that may result from error in image generated algorithm or image process. First, we put color image in convert to a gray cell image. Gray cell image simply computations and highlight the structure features of the image. The canny edge detection algorithm is used to find strong edges in the image by calculating the gradients of gray cells image. The second part is boundary fuzzy detection. We apply Gaussian blurring to the image allows for the analysis of edge blurriness. Gaussian blurring smooths the image through convolution. Significant changes suggest sharp edges. Since generated image may exhibit unnatural edge blurring, this serves as an effective feature to distinguish real images from generated ones. And we use typical CNN architecture, including input image, convolution layer, pooling layer, fully connected layer, and opt layer. The model extracts image filter layer by layer, and finally computes the classification text through the fully connected layer and the output layer.
To start, our system builds a bimodal modeling architecture, which means we combine CNNs with manual feature extraction. The combination of these two techniques allows the model to detect image authenticity more accurately, while reducing reliance on a single type of image. This makes the system adaptable to various environments. In the process of building the model, the first step is to handle the CNN image processing pipeline. This pipeline begins with an input layer where image data is received and then passes through several convolutional layers to extract deep features. After that, a flattened layer converts these features into a one-dimensional vector. Next, we have the manual feature processing pipeline, which starts with the manually extracted features. These features are reshaped using a reshape layer to ensure they are in the correct form for further processing. Then we move to the weighted fusion of features in the model. The CNN features are assigned a weight of 0.9, and the manually extracted features are given a weight of 0.1. This ensures that both sets of features contribute to the final model. These features are then fused using a concatenate layer, followed by a fully connected layer with a sigma-mode activation function, which performs binary classification to determine whether the image is real or fake. These two functions are the functions that used in our model, the ReLU function and the sigma-mode function. The main function is the entry point of the program, and it handles everything from data loading to model training, evaluation, and visualization of results. The process includes loading the dataset, normalizing the images, splitting the data into training and test sets, building the model and training it using model fit. The trained model is then saved and evaluated, and we visualize the changes in accuracy and loss during training. Finally, the model is tested on some sample images, displaying the true labels and the predicted results. Now, let's move on to the outcome of our project. First, in terms of test accuracy, the model achieved 90.76%, demonstrating strong classification performance in distinguishing between real and fake images. Training accuracy increased rapidly at the beginning and eventually stabilized at around 95%. Although the test accuracy is slightly lower than the training accuracy, it still exceeds 90%, indicating good generalization on unseen data. The accuracy trend line of both the training and the test sets gradually converge, showing that there is no significant overfitting. Next, these are some samples, our outcomes. Next, regarding the loss function, the training loss decreased sharply after the first few iterations and remained stable at lower values, indicating that the model is effectively learning meaningful features. The test loss followed the same trend, eventually stabilizing at a low level. From the loss variation graphics, we can see that the training and the validation loss curves are closely aligned, further confirming that the model doesn't suffer from significant overfitting. In conclusion, by building a bimodal model architecture, we successfully developed a highly versatile image authenticity detection system that combines manual and automatic feature extraction to achieve more accurate detection results. This system reduces reliance on a single model, making it more adaptable. Overall, the model shows favorable trends in both accuracy and loss on the training and test sets, proving its effectiveness and robustness in the task of image authenticity detection. Thank you.